Hello everyone. Today we will talk about the inverse Z transform. And we use the inverse Z transform to get the signal back in the time domain or in the spatial domain. For example, I may have a system with h of z and I can find the Z transform for the input x of z, then it's easy to find the output. It's just the multiplication of the transfer function with the input. But the output in this form, the Z domain, will not make sense to me in the sense of hearing it if it was a speech signal or seeing it if it was an image signal. So then we use the inverse Z transform to find y of n. Now the definition of the inverse Z transform is this equation, where you have the signal in the Z domain, you carry out these contour integrals, you find the signal in the discrete time domain. But these contour integral involve the knowledge of complex variable theory, which we usually study in graduate school. So for now and for this course and for undergraduate, usually we use partial fraction expansions to find the inverse Z transform. For example, we may have y of z equal z squared plus 3z over z cubed plus z squared minus 5z plus 3. So now we do partial fraction expansion to express these as a simple linear sum of expressions that exist in the table, like this one. And then we can use the table to find the inverse Z transform and find the signal x of n in the discrete time. So we're going to demonstrate the inverse Z transform by examples. And there are 4 situations. One, when the characteristic roots here are distinct real. The second scenario, when you have repeated characteristic roots. The third scenario, when you have complex characteristic roots. And the fourth example, we will find the inverse Z transform of a signal that has both causal and non-causal part, or a signal that exists in negative n and positive n. Okay, so let's start with the first example here. When we factor out the denominator, we will have distinct roots. So let's write xa of z. The first step, by factoring out this quadratic equation, it will come as 8z Now this will be a over z minus 3 plus b over z minus 2. And when I solve for a and b, I will have constant. But in the table, I have in the numerator z. Here, gamma is the 3 or the 2. So in order to have z in the numerator, what we can do is divide this term by z and also this by z and this by z. Now when I do the partial fraction expansion of this term, it will be a over z minus 3b, but then I will have a third term for this z, c over z. Now I need to find a, b, c, all these 3 constant. So let's work out with this. So x of a z equal. Now there are many ways to find these constant a, b, and c. One way is if I multiply this side and every term here by the denominator of a and set z to equal 3, this will disappear, and only a will survive. Then I can solve for a. So let's do that. Then this will be So when I plug for z 3, this will be 0. When I plug for Z3, this will be 0. This will cancel this, so I have A by itself here. Now this will cancel this. And now I'm gonna plug for Z3 in these terms. So then 8 times 3, that will be 24 minus 19 divided by 3 minus 2 times 3. And that's equal A. So from here, A equal 5 over 3. Same thing, to find B, multiply everything by its denominator and then set Z to equal 2. So if I do this, then this will be 8 of Z minus 19 over Z minus 3 times Z. I'm not going to write Z minus 2 because it will cancel since I multiply everything by Z minus 2. Then I set Z equal 2. Same thing, when I multiply this by Z minus 2 and set Z to equal 2 will be 0. For this term, multiply by Z minus 2, I will have only B. For this term, again, if you multiply by Z minus 2 and set Z equal 2, it will be 0. So B will be... Now to find C, I'm going to multiply everything by its denominator. Then it will be so this cancel, and here I will have minus 19 divided by, here is 0, that will be minus 3, 0, that will be minus 2, equal. You plug for Z 0, that will be 0. Same thing here, 0. And this will cancel, and I will have here C. And from here, C equal. So I found all these constant. So now let's rewrite our equation, which is this, equal these terms. So let's rewrite it down here. A, we found it to be 5 over 3 plus B plus C. Now I can bring these up here and here and here, and I got exactly this form that exists on the table. So the inverse of this then will be this one. So x of AZ equal plus. Now I can use the table to find x of A n. This is 5 over 3 constant, and the inverse Z transform of this one, let's clean up this. If I compare this to this quantity here, gamma is 3, so then the inverse will be gamma n. So that will be 3n u of n. Plus this one will be 3 over 2. Again, here gamma is 2, so that will be 2n u of n. Now this Z over Z is 1. So I will get minus 19 over 6. The inverse Z transform for 1 is a delta. And this is the answer. So this is exactly the same as this one here. Now you could have solved it without dividing by Z to create it in this form. I could have solved it this way. I could have just said this equal A over Z minus 3 plus B over Z minus 2. Then I solve for A, I solve for B, and I will get a constant. And A will be 5 over Z minus 3, and B will be 3 over Z minus 2. Now, I don't have this in the table, or this one. So I can manipulate this term by saying this is 5Z over Z minus 3 times Z minus 1 plus 3 Z times Z minus 1 over Z minus 2. See, Z times Z minus 1 is 1. So this term will be exactly here. But then I have to use the time shift property, which is shifted by n minus 1 and n minus 1 here. And this term will come exactly the same as this term. If you plot it, the same. Okay, let's do another example where the poles or the roots are repeated. So let's clean up. in this example, when I see z minus 2 to the power of 2, there is repeated roots. That means z equal 2 and z2 equal 2. In the z domain, we call them poles. So when we have repeated, then we have to make sure to include all possible scenario. So this term then will be, I'm going to take this z first in the denominator here. So I'm going to rewrite this as okay. The first thing before you do the partial fraction expansion, make sure z in the denominator is at higher power than z in the numerator. So for this example, we have no problem because in the denominator, if I multiply all these terms, I will have z cubed. This is z squared times z, that's z cubed. And in the numerator, I have z squared. So we have no issue. But if z in the numerator and the denominator have the same power, or z in the numerator has larger power, then you have to do long division first until you get an expression where z in the numerator has less power than the denominator. So for this example, we have no issue. So I will do the partial fraction expansion. So this will be x b of z over z equal a over plus b z minus 2 plus c over. If that was q, then I will have another term here, z minus 2 to the power of 3. So you have to include all lower power since we have two repeated roots. So we will have two terms for each root. All right, to find a, multiply by z minus 1 and set z to equal 1. So then this would be and a will be 3. Now here we have issue. Should we find b first or c? Well, it's easier to find the constant that has the highest power in the denominator. In this case, it's the c. So to find c, multiply everything by z minus 2 to the power of 2 and set z equal 2. So in this case, when I multiply this by z minus 2, so let's do it in detail. Okay, these will cancel, so the c will survive. Now here, one of them will cancel one here, but then when you plug for z2, that will be 0. Same thing here. This cannot cancel anything here, so plug for z2, that will be also 0. And this one will cancel here. Here you have to evaluate z equal 2. So when I plug for z2, I will have 2 times 4, that is 8. 2 times 11 minus 22 plus 12, divide 2 minus 1 is 1, equal c. So from here, c equal minus 2. And from here, a equal 3. Okay, so now how do we find b? Well, if I say the same thing, multiply every term by z minus 2 and set z to equal 2, I will have problem here. Because when I multiply c by z minus 2, only one cancel. Then when I plug for z2, that will be 0. Anything divided by 0 is undefined. So the best way, since I already know a and I already know c, I have only one unknown. I just plug any value for z and solve for b. So let's clean up. So this term equal this term. I can plug for z1. No, 1 I cannot, because 1 minus 1 I get 0. So the easiest one, I plug for z0. So if I plug for z0, whatever I get here must equal these terms. Okay, so 2 times 0 minus 11 times 0 plus 12. So I'm plugging for z0 here. Equal. Now I have to plug for z0 here. So that will be a over, and a, I know its value, it's 3. So let's replace it by its value. Plus, now I plug for z0 here. b over plus, now this term, c I already know it's minus 2, and plug for z 0, that will be 0 minus 2 squared. And from here I will get 12 over minus 4 equal minus 3 minus b over 2 minus 1 over 2. And if I multiply everything by 4, I will have here minus 12. And solve for b, b should be minus 1. Okay, after we found all the constant, now I go back to this problem. And I plug the value for a and b and c. So this will be, let's write it here, x, a is 3 over z minus 1, b is minus 1, and c is minus 2. So I am rewriting this here. And xb of z will be, now I'm going to bring these 3 up here and here and here. So multiply basically everything by z. So you will get 3 z over z minus 1. And I will use the table. I'll be using these two items in the table. Let's clean this. xb of n. The inverse z transform of this one will be 3 gamma is 1 n u of n. For this one, minus gamma is 2. For this term, I'll be using this. So this term here, I can write it this way. So gamma this is 2. And here it's 2. So then the answer will be this, minus n to n u of n. And I can simplify this further. 1 to the power of n is just 1. So that's 3 u of n. And I can take u of n outside for all of them. So this will be just 3 minus 2 to the power of n u of n. And if I need it to be in this term, then I can say 3. I will take 2 of n here as a common factor. So that will be minus. What's left here is 1. What's left here is n u of n. Okay. So this is an example for repeated roots or repeated poles. The third example is when the roots are complex, like this. So let's clean up first. Okay, in this example, there are different ways to solve it. Let's solve it so we can use this property. So I can express this as follow. I'm bringing this z in the denominator here, like a cross product. And this will be now, when we factor these, we will discover that it has a complex root. And we use a calculator or the quadratic equation, we will find it to be the following. And the next one will be the conjugate. So it will be z minus 3 minus j4. Now, if you are comfortable with complex number, we can factor out these as follow. Now we can follow the same step as before to find A and B and C. If you are comfortable with complex number, so to find A, multiply everything by its denominator and then set Z to equal 1. If we do this, then this term here will be, this will be cancelled. So I will have only Z minus 3. When you multiply this by z minus 1 and you set z1, this will cancel. Same thing here. This will also cancel. So the only thing left is a. Because when you multiply this by z minus 1, it will cancel with the denominator. And if you plug for z1, this will be 3 times 1 is 3 plus 17, that's 20. 1 and minus 3, that's minus 2. So A equal to E. Now, how do we find B? Same thing. To find b, multiply everything by its denominator and set z to equal 3 minus j4. So then this equation now will be as follows. Since I'm multiplying by this term, this will be cancelled. So I will have only and everything evaluated at z. Now when I multiply this a by this term here and then set z equal this will be 0. And also this will be term 0. So I will have only left here is b. So now let's plug for z this value. And b equal 52 minus j24 over, I can divide numerator and denominator by 4 to simplify it further. So this will be 13. So I divided by 4. Now, in this table, this is in polar form. So let's express this b in polar form. So that will be 14 point. Now I used in the calculator, this is in radians, divided by. Now you have to be a little bit careful when you find the angle of this vector. Students usually make a mistake. Best way, draw this vector. So if you draw this vector, it's real, it's minus 8 here. The imaginary is minus j4 here. So the vector is here. And now you have to find the angle here. Because if you just use the calculator, you're going to say tan inverse, the imaginary minus 4 divided by the real minus 8. This is the same as tan inverse 4 over 8. And that angle will be, the calculator will give you this angle. So then how do you find it? It's what the calculator give you. Minus 180 and you will get this, which is minus 2.68. And b equal, if you divide, it will come out to be 1.61. Now the good thing, you don't need to find c. Why? Because c will be always the conjugate of b. So I can confidently say c will be 1.61 e minus j, 2.25. This is the conjugate of this. It has to be because then x of n has to be real. So now we found all the constants. Now I can go back to the problem here and say the following. X of c divided by z equal this. A, we found it 2 over z minus 1 plus b, we found it here. So that will be 1.61 over this. Plus now this term c is this term here. Okay, still have to do something because if I need to use this item in the table, this quantity here and this quantity here has to be expressed in polar form, which is not a problem. This will be 2 over z minus 1 plus here I have to have the 0.5. So I can multiply this by 2 and by 0.5. So if I multiply this by 2, it will be 3.22 0.5 EJ 2.25. If I multiply this 0.5 times this, I will get the 1.61 Z. So now I can rewrite this as minus 3 minus J4. And then if I find this in polar form, the magnitude is 5 and the angle will be minus 0.93. So now I can delete this and write it in the polar form. 5 plus. Now this one term here will be exactly like this term, except conjugate. So it will be 3.22 2, 2. And here it will be the same as this, except conjugate. Let's clean up a little bit. So now let's rewrite this equation again here. And I'm gonna bring z now in the numerators here. So this will be x of c, z equal 2 plus okay, so now let's compare it to here. So x of cn will be, this is very simple. We used it in the previous, so that will be 2. Gamma is 1 and u of n plus. Now I can take this 3.22 here out. Now when I compare these terms to this term and here to this term, because here j beta will be this one, j 0.93 positive. So by this comparison, beta equal 0.93, gamma equal 5, theta here equal this one, minus 2.25. Then the inverse z transform for these two terms will be this. So it will be gamma, which is 5 to the power of n, cosine beta, which is 0.93, and plus theta, which is negative. So that should be negative 2.25 u of n. And this is the answer. Again, this 1 to the power of n is just 1. So if I rewrite this one and take u of n as a common factor, then this will be just same as this one. Now there is another way of solving this problem if you are not comfortable with the complex root. All you have to do is factor out these in this form. Let's clean up. Factor out these. And then this will be a over z minus 1 plus little a z plus b over these terms. And you can find a the same way we did here in these problems, but then you have to solve for little a and little b. When you determine little a and little b and it is in this form, now you use the table. You use this item in the table. You found a, you find b. This is given to c and gamma, that's the quadratic equation. And now using this quantity, little a, little b, and the c, and the gamma, you calculate these terms. And then you plug it here, and that would be the inverse z transform of this one. It is still involved these calculations. Complex, if you are comfortable, I think it is easier because you don't need to calculate b and c. If you know what is b and you calculate it, then c will be the conjugate. Same thing here, the characteristic roots or poles, they are conjugate of each other. So you really just do one calculation. Okay, the last example involves a z function, but it's unilateral and bilateral. That means it exists for positive n and it exists for negative n. Then how do we handle it? In the previous examples, we assumed it's all unilateral. That means the signal exists for n equal or larger than 0. And that's why in every answer we have u with n to indicate that it is unilateral. It exists for positive n. And the same here in this answer. So how do we handle a situation where the signal could be bilateral? It may have positive and negative. Well, let's demonstrate this concept by solving this equation. But before we do that, let's clean up. In this example, we have x of z, but we are given a region of convergence. So in one scenario, z is larger than 2. In another scenario, z is less than 0.8, and the third scenario, z between 0.8 and 2. So let's first find the inverse Laplace transform for a region of convergence z is larger than 2. So first step, bring this under x of z. Then express this one as a over z minus 0.8 plus b over z minus 2. And now we need to find a and b. Same as before, multiply everything by z minus 0.8 and set z equal 0.8 to find a. This will cancel this. Then plug for z 0.8. This will be minus 0.8. This will cancel this, and you have here a. When you plug for z 0.8, this will be 0. So from here, a equal 1. And same thing to find b. I multiply everything here by z minus 2. So what's left will be minus z plus 0.4. When I multiply by z minus 2, this will be cancelled. So I will have here z minus 0.8. Then let z equal 2 minus. So x of z divided by z equal a, which is 1 divided by z minus 0.8 plus b, which is minus 2 divided by z minus 2. Now multiply every component here by z. I will have x of z. Okay, this is a partial fraction expansion. Okay, now for this part, z is larger than 2. The region of convergence, if we plot it, the first root is at 0.8. The next one is at 2. So if we draw a circle here, and z here is larger than 2, that means this is the region of convergence. It's outward. So for this term, it's outward, and for this. So that means the signal in the time domain for both of them is causal. Exists for n is positive. So x of n in this case will be 0.8 n u of n. So that's from the table, minus 2. And for this, it's 2n u of n. This is the answer for part A. Now for part B, c is less than 0.8. So the solution will be the same up to this point. But now when I do the inverse z transform, I have to look for the region of convergence. So let's plot here. This is 0.8, this is 2, and region of convergence is inward since z is less than 0.8. So this is 0.8. So in this case, x of n exists for negative n. So it's anti-causal. So then from the table, x of n will be, let's call this xb of n. If I look in the table, this term will be minus 0.8 n u of minus n minus 1. And same thing for this one, that will be minus 2 of n u minus n minus 1. And minus times minus, that will be positive. So let's just delete it and make this positive. And this will be this answer. Now for part C, the region of convergence, the magnitude of z is larger than 0.8 and less than 2. So if we plot the region of convergence, this is 0.8, this is 2, and region of convergence is in this region. So now for this term, the region of convergence is outward. So this will be a causal signal, exists for n positive. So if I call this xc of n, it will be 0.8 n u of n minus. Now for this term, region of convergence is inward. So this will be anti-causal. It exists for negative n. So it will be minus, the 2 here will be here, and then gamma is 2n u of minus n minus 1, since it's anti-causal. And minus times minus, that's plus, so let's write it positive. And this is the answer. So the steps are the same, the partial fraction expansion, but then the region of convergence will determine if the signal is causal, exists for n positive, or anti-causal, exists for negative n, which means you will be using in the table either for z larger than gamma, then this will be the inverse. For z less than gamma, then the inverse will be this one. Okay, let's go back. So this ends the video for inverse Z transform. Thank you for watching and see you in the next video, and we will be talking about property of the Z transform that will help us for system analysis. Thank you and see you next video.